All right. Hello again, everybody. I'm back for the next few weeks. Today I want to finish off minimum spanning tree. Most of today's lecture is going to be devoted to the union find data structure, which I believe you've already seen in 61B. Is that right? But I'll cover it. I'll cover some more advanced tech for union find or for the analysis of it. So right before midterm 1, you saw an algorithm for the minimum spanning tree, which is Kruskal's algorithm, which I believe you've also seen in 61B, right? Which I've written. I don't want to spend too much time on this because you saw it already. You saw it last week. But we assumed that basically what we did was we grew components locally, right? So initially we just said every vertex is its own connected component. And then we sorted the edges in increasing order of weight. And then in increasing order, we went over the edges one by one, and we asked ourselves, does this edge unify two components that are now separate from each other? Or are they already the same? Or are those two vertices already in the same component? Right? And if they are in different components, we merge them using this edge, and we throw that edge into the spanning tree, into the MST. So that's exactly what this is doing. And Professor Chiesa, a week ago, introduced these three operations, make, set, find, and union. Right? And those three things appear in the pseudocode for Kruskal. So I don't want to dwell on that. You've already seen this algorithm. I want to dwell more on how to actually implement these operations. Okay? So now we're focused on a different problem, a data structural problem. Okay? And the data structural problem, I'll call this problem the union find problem. Okay? What is the union find problem? You would like to maintain a collection C of disjoint subsets of 1 to n. Okay, so C is a set of sets. And the following three operations are allowed. So you can make set on X. X is something between 1 and n. And what that does is it adds a singleton set to C, which is the set that only contains X. Right? So that's the first thing you do in Kruskal, right? Because every vertex is its own connected component. So basically you have a set that only has that vertex. So initially, right after you did this make set, all these make sets in Kruskal, your collection is n different sets. Each set just contains a single number. So there's a set just containing 1. There's a set just containing 2, etc., up to n. Find returns the name of the set containing X. So for me, Sx, maybe I should consistently, here I put parens. So later I didn't put parens, so I'll call it Sx. S sub x is the set that contains x. So find for x should return the name of the set containing x. What is the name? It doesn't, the problem definition for union find doesn't really specify what the name should be. All I care about, my requirement is that the name is consistent across the set. So like no matter who you find in that set, you should always get back the same name. There should be some canonical name. Okay. For us, the name will always be some representative element from that set. Okay. And union, what union does is, if you union two elements x and y, it looks at, there's the set that contains x, there's the set that contains y. Okay. It gets rid of both of them, it drops both of them from C, and it adds to C the set with the union of those two sets. So for example, if there's the connected component that contains x, the connected component that contains y in Kruskal, when you do a union, now you've basically merged those two into the union connected component, right? Because you took an edge that connected these components together. Okay. So this problem is a data structural problem that's well defined, independent of Kruskal. Like this, solutions to union find get used in Kruskal, but that's not the only place they're used, right? Just like, for example, binary search trees get used in some applications that they're not defined by just that application. They're widely used, right? So you should view this as a widely used data structure that's not only important for Kruskal. So for example, we might give you questions on a homework or on an exam or whatever where you might have to realize that you can solve the problem using union find in a way that has nothing to do with MST. Okay. So I want to talk to you for the first part of the lecture about how to solve union find. Okay. And I know many of you, again, have seen this in 61B. You've seen this. There's a solution called the disjoint forest data structure. Okay. I am going to get there, but I'm not going to get there from the beginning. I want to start somewhere else. Okay. So solutions for union find. So I always like to consider like what's the most naive solution that doesn't require me to think a lot. Okay. So let's say really naive is, let's say, an array where AI stores the name of the set containing I. And what is that name going to be? As long as it's consistent, it doesn't matter. So for example, I could set the name of the set to be the smallest element in the set. Okay? And if the thing is not actually in the collection yet, if it doesn't participate in any set in the collection, I'll store null. Okay? Now, how would I do find? I just look at AI. How would I do union? So if I do union AB, I look at the eighth entry of A, I look at the bth entry of A, right? Okay, if those two values are already the same, they're already in the same set, I don't have to do anything. But if they're different, let's say the name of A set is T, and the name of B set is U. I scan the array, I find everyone who's either a T or a U, and then let's say T is smaller than U. I replace all the U's with T's, right? That's it. So that's linear time because I have to scan this array. And then make set is also constant time. Right? I basically just replace AI was null before. Now AI is I, because I is in a singleton set by itself. So this is a very straightforward solution that's not fancy. It's always good to keep in mind that you don't have to jump into the fanciest stuff first. Okay, so this works. And it would give you an implementation of Kruskal. So you have to sort the edges in Kruskal. That takes m log m time. And then how many finds, unions, and make sets do you do? You do something like m finds. You do something like n make sets. And then you do at most n minus 1 unions, right? Because every time you do a union, you decrease the number of connected components by 1. So you do something like linear number of unions. So n unions, each one costs you n time. That'd be n squared. So the runtime would be m log n plus n squared. So this gives a valid implementation of Kruskal, right? It's just not the fastest because you could do disjoint union. You could do union find faster. So let's try to do something faster. And actually, what I'm going to show you now is an algorithm that a data structure to solve union find, which will actually remember you're already spending m log n time just to sort the edges, right? Notice I said m log n instead of m log m. Why is that okay? Just so we're all on the same page. Yeah, m is at most n squared. So log of m is at most log of n squared, which is at most 2 log n. So log m and log n, basically log m is big O of log n. Right? So m log n, it's all the same, up to constants. So I'm already spending m log n time sorting the edges. So as long as whatever I do in here takes less than m log n time, I'm golden, right? So I'm going to show you that, in fact, it's possible to, not even using the disjoint forest data structure, something much simpler, solve all this stuff in much less than m log n time, which is already good enough for Kruskal. And then I'll show you the disjoint forest data structure, which does even better. But it does better, but that's not useful for Kruskal, because Kruskal's bottleneck is the sorting anyway. It could be useful if, for example, you know something about, maybe you're sorting numbers that are small, so you can do the sort faster. Then that maybe what happens later matters, right? But if you're just doing general comparison-based sorting, you're spending m log n time to sort the edges. Okay, so here what we're going to do is represent sets as linked lists. linked lists. Okay, so make set. How would I make set? I would just allocate allocate a new node. And have some array of pointers point to it. Right? So the picture you should have in mind here is there's some array A of length n. This is my array A. And each entry here, AI, is just a pointer to some linked list node that represents item I in my collection, or item I in my universe. Okay. Of course, now, I said I'm representing sets as lists, so over time, these linked list nodes might start pointing to each other. And in fact, let me make it a doubly linked list. So over time, what the picture looks like is I'm representing my collection I'm representing my collection C as a collection of separate linked lists, of like disjoint linked lists. So I represent C as, here's one linked list, here's another one, here's a longer one, etc. So here I have 3 sets in my collection. Okay, so now if I wanted to implement, say, find, given that I'm representing sets in this way, what's a natural name to assign to a set? The head of the linked list. It sort of, stands out to me. Or the tail, let's say the head. So return the item corresponding to the head of X's list, linked list. And then union right? So if I want to union 2 linked lists, what do? I walk to the head of one, I walk to the tail of the other, and then I make this head point to this tail. So walk to the head of X's list and make it point to the tail of Y's. Okay? So this is where I'm using a doubly linked list. From Y I'm walking down, from X I'm walking up. And let me just note right now, because I'm going to use it in an optimization that I'm going to discuss soon, I could also make it singly linked, where I only have pointers going forward toward the head. And then I could also maintain the invariant that the head node remembers who his tail is. Right? And I can maintain that fact under unions. Right? So he knows who his, so basically Y goes to his head. The head remembers who the tail is. So now I have the tail. Also X goes to the head. And this head knows who his tail is. Now that I did the union, I can update his tail to be this, because I know this, because I know it from him. Okay? So let's say it can even be singly linked, where the head has a pointer to its list's tail. Okay, so what are the runtimes here? This looks like, worse than this. So find is linear time, because I have to walk to the head of my list, which might be really deep in the list. Union is also linear time, because to do a union, I have to first do a find to walk to the head. And then make set is constant time. Right? So what I've described so far is slightly worse than the naive, just vanilla array thing. But let's try to make it faster. And the way I can make it faster is to try to develop some kind of heuristic. Look at where I'm spending a lot of time and see whether I can reduce that time somehow with something simple. So find, I said, is slow. So what did I say? I said union is slow, find is slow, make set is not bad. Let's try to make find faster. Find is slow because everyone needs to walk all the way to its head of its list when I do a find, right? Why don't I just do the following thing? Every node will also just store a pointer to the head of its list. So tweak every node stores a pointer to the head of its list. Okay. So what goes wrong here? Right? What goes wrong is that when I do a union, that means everyone here has a pointer to its head. Everyone here has a pointer to its head. When I do a union, all these people have to change their pointers because they're now in a new list with a new head. Right? Okay. So union is still going to take me linear time, but now find at least is constant time. So find and make set are down to constant time. Now one more tweak to get it even faster. Notice that I had two options. I could have made this list go underneath this one, point to this one's tail, or I could have done it the other way around. I could have made this list, this head, point to the tail of this list. Either way, I get the same set. Right? In this example, which is better? Would I prefer to make the left one point to the right or the right one point to the left? You can maybe scream a little louder. Who says the left one should point to the right one? Who says the right one should point to the left one? Okay. So, in fact, I prefer, in this case, the left one point to the right one. Why? There are only 3 nodes here, whereas there are 4 nodes here. Right? If I make this one point to that one, I have to update the head pointers for 3 things. Whereas if I make that one point to this one, I have to update the head pointer for 4 things. Right? So I prefer to make the smaller one point to the tail of the bigger one. Because that's fewer updates for me, right? So tweak 2, make the smaller list point to the tail of the bigger one during unions. Okay? So if you do these 2 things, then I claim, right? And how can I implement this? How do I know the size of the lists, right? I can also maintain the invariant that the head node of a linked list remembers the size of its list. Okay? I'm only going to maintain that invariant for the head. And that I can also maintain, right? When I do make set, the size is 1, I set it to 1. When I do find, the size doesn't change. When I do union, let's say that's the head of the whole thing now. I just take his size and add in what he said his size was, and I've maintained the invariant, right? So that's that's information that I can maintain easily. Okay. And the claim is that any sequence of at most m finds and at most n make sets and unions takes total time O of m plus n log n. That's the claim. I'll prove that to you. But think about what that means for Kruskal's algorithm. Right? When do I do a find? For each edge, I do 2 finds. Right? So I do 2 m finds. I do n make sets. And I do exactly n minus 1 unions, because every time I do a union, I decrease the number of components by 1. So what this says is that that whole for loop takes m plus n log n time, and then the sorting is already taking me m log n time to sort E. So sorting is still dominant, so my overall runtime is m log n. Right? So you don't actually, for Kruskal's algorithm, this means you don't actually even need the disjoint forest data structure to get m log n time. You can just use this very simple thing with linked lists. I mean, the disjoint forest data structure is not that hard to implement either, right? But you don't actually need it for Kruskal. Okay? So why is this claim true? So proof, basically proving this claim. Now, let's just think about what happens here. When I do a make set, I allocate a new node, constant time, right? When I do find also takes constant time, because remember, everybody stores a direct pointer to its head, right? So find is constant time. When I do union, y has to know y takes the pointer to its head, which then gives me its tail. X takes the pointer to its head, which then can point into the tail. All of that is constant time. But then I have to spend more time changing the head pointers of everyone here. Okay? So the total time is O of m plus n plus the number of times I have to change some node's head pointer. Right? Over all operations. This is not time per operation. This is the aggregate time of doing all the operations. Right? So for each of the m plus 2n finds, make, set of unions, I'm doing constant work, plus there are some times when I have to do extra work to change someone's head pointer because there was a union. Right? So that's what this is. This is all the times I change someone's head pointer due to a union. So let's zoom in on this thing. Let's just kind of do some accounting and break it up into summing over whose head pointer I changed. So this is the sum over all I goes from 1 to n of the number of times we changed i's head pointer. Right? Every time we change a head pointer, we're changing someone's head pointer. So that change is getting counted for some I here. Okay. Now let's look at this. What does it mean that I changed i's head pointer? It means that I did a union that involved i's set. Right? So I unioned one set with another, and I was in the smaller set. Right? Because you only change the head pointers of the people who got moved below the tail of the other set. And you do that to the smaller set. Right? Okay, so let's think about this. I started off in a set of size 1 at some point when I did make set on I. Right? And then I did a union where it was in the smaller set. Which means now it's in a set of size at least twice its old size. So it went from being in a set of size 1 to being in a set of size at least 2. Right? Its new set size has to be at least double if it's on the smaller side. And then the next time I changed its head pointer, again it was on the smaller set, which means from a set of size 2, it now is in a set of size at least 4. And then the next time I do a union where I have to change its head pointer, it went from a set of size at least 4 to a set of size at least 8. Right? Every time that I'm changing its head pointer, it's because it's now in a set that's at least double the size of its previous set. How many times can its set size double? Well, the universe has size only n. So its set size cannot double more than log base 2 of n times. Which means for any I, the number of times its pointer to the head of its linked list changes can be at most log base 2 of n. So in total, this is O of n log base 2 of n. In fact, it's at most n times log base 2 of n. Right? So good. The total time is m plus n log n. That's it. Okay? So it's not that crazy. Okay? Any questions? You already now have seen an implementation of Kruskal together with a full analysis that is m log n time. Right? You didn't even need to see disjoint forest. Okay? Now, I do want to tell you about disjoint forest. And again, I like to explain algorithms in a way where I don't just give you the code and then analyze it. I want you to understand where that data structure even came from. Okay? So where did disjoint forest come from? Well, so let's say now 3 disjoint forest. Okay, so what is the data structure and where did it come from? So here's the idea. Right? Now that you're all experts in reasoning about big O, let's go back to the vanilla linked list implementation, okay, where I was actually following pointers until I got to the head. How would someone come up with disjoint forest? So the point is there's this linked list here, collection of linked lists. Now, if I do a find, okay, if I do a find on, let's say, this node, I spent time looking at 3 nodes, right? I start here, I walk to here, I walk to here. So since I'm already spending, let's call it 2 nodes plus the root. So since I'm already spending time looking at these 2 nodes plus the root, I already spent 2 time. I can afford to do 2 more units of work basically for free under big O notation, right? Because if I do, let's say I looked at 7 nodes. And then if after looking at those 7 nodes, walking 7 nodes up to the root, I do 7 more units of work, I've only doubled my total running time, which in big O notation is the same, right? Instead of 7 time, I did O of 7 time. Okay, that's bad form, but you know what I mean. So what might I do? What's one natural thing to try to do to kind of make my job easier the next time I want to do a find? Remember now, what I said was, finds, before I said everyone stores the name of the head. I mean, everyone storing the name of the head is a little complicated because sometimes you have to change a lot of people's pointers, right? So I don't want to have to change everybody's pointer. Even this solution, which got n plus n log n, I want to somehow do better, right? So I want to avoid having to change everybody's head pointer during a union. So let's not have everyone store a pointer to its head. But what I'll do is, I've already spent 2 units of time looking at these 2 nodes. Why don't I just now make them for the future directly point to the root? So it's not going to be a linked list anymore, but it's still going to be some kind of nodes with pointers pointing to stuff, and kind of the root will still be the name of the set, right? So here's the idea. So now I look at these 2 nodes. Since I spent 2 units of time looking at them, I can afford to spend 2 more units of time changing pointers. So what I'll do is I'll make sure that these 2 nodes point directly to the root. So now this guy points directly to the root, and this guy was already pointing to the root. Which means the next time I do a find from him, I just immediately get there, right? So I've saved time. I basically am making shortcuts for the next time around. Okay? And then again, I might do unions. When I do unions, since we're not dealing with lists anymore, because after you do a bunch of these, for example, if you also do a find on him, he's now going to point directly to the root. So this picture now sort of looks like this. Well, it looks exactly like this. Right? Because now these 3 people are pointing directly to the root. You've changed their pointers to point directly to the root. And then now maybe you want to do a union with another set. Well, the natural thing is either this person is going to point to him or this person is going to point to him. I have to choose who the new head is going to be. So let's say I'll make this person, let me draw it a little bit lower, I'll make this person point here. So if I do enough of these finds and unions, at the end of, what do my sets now look like? They look like trees, right? They're not lists anymore, they're trees. So this motivates the idea of let's start thinking about allowing our sets to be represented as trees instead of as lists. Because if I do this heuristic, which by the way is called path compression, so this was called the path compression heuristic. Path compression is whenever I do a find and I walk up to the root, everyone I touched now points directly to the root. That's path compression, which you've seen in 61B, I think, right? You've seen that in 61B? Yeah. So that's path compression. So you can get this whole disjoint forest idea by thinking about doing a path compression heuristic on linked lists. Okay. So now let's try to think about more heuristics we could do with lists, with trees, sorry. So, heuristics for trees. One we said was path compression. That's what got us to this whole tree business in the first place. And then the next one, we did this thing for linked lists where we did union by size, right? We took the smaller list and we made it point to the bigger list, right? And the reason we did that was because we would have to change fewer head pointers. So now the natural thing I would say is probably union by height, right? Because if you have trees, then what's the running time it takes to do a find? You basically have to walk from wherever you are at to the top of the tree. What's the worst case? The worst case is where you're very deep. So naturally, I want to keep these trees shallow, right? So if I have a really tall tree and a really short tree, if I make the tall tree a child, so this is the root here and this is the root here. If I make the tall tree a child of the short tree, I'm going to increase the height by 1, right? Because, here's the short tree here. Now it points downward like that. I've increased, this used to have some height. Now the height is this plus 1. Whereas the alternative is that I just have that big tree, and I make the short tree point to it. Now the overall height hasn't changed. Of course, if they have the same height, there's nothing you can do. One of them it's going to get increased by 1. But if they have different heights, it seems that I want to make the short tree, the root of the short tree, I want to make that root point to the root of the big tree, the deep tree. So it's not really about size anymore. The natural analog now seems to be height. Okay. So a natural heuristic also is union by height. Okay. And you can actually analyze them separately. So you can say, forget about path compression. Let's just do trees where I do union by height. Okay? What kind of running time would I get? You could get actually that same kind of analysis. Okay? You could also say, let me not do union by height. Let me just do path compression. What would I get? You would also get a similar kind of analysis. Okay? It turns out that you can do both when you put them together. Do even better when you put them together. And already there's a problem here, which is how can you really put them together? Because how can I do union by height? Basically, just like with linked lists, I said the root of the linked list, the head of the linked list, will remember its size. So let's try to do the same thing here. The root of the tree remembers the tree's height. Okay? Now, when I do unions, if I union trees of different sizes, and I make the deeper tree the new root, the height doesn't change, right? So that's fine. I don't even need to update the root's height field. When they have exactly the same height, then the height field increments by 1, right? So that can be maintained. The problem, though, is what about now when I throw in path compression? Right? I could have a tree that's really deep, but then I do a bunch of finds, and after I do a find on every single thing in the tree. What does that mean? That means all of them now point directly to the root. So now the tree is extremely shallow. Right? Everything is pointing directly to the root, which means its height is 1. But how do I know that? Right? If my invariant is that the root remembers the height of the tree, then how can I maintain that invariant? How can I maintain that knowledge subject to path compression? You can think about it offline, but the problem is you really can't efficiently. Right? Because maybe the reason that my depth of my tree is d is because there's some particular branch that's deep. But if I do path compression on that branch, then how as the root do I know that I don't have some other branch that's also depth d? Unless I look at all my children and figure it out again. But that takes time, right? I don't want to have to take time to update my height field. I want to just know it, in constant time after every operation. And path compression ruins that, right? Path compression makes it hard for roots to keep track of their heights. Okay. Questions? So I'm not going to do, if I want to combine them, I'm not going to do union by height because I can't afford to keep track of the height. It's too expensive. It's too costly in time to keep track of the height. So instead what I'm going to do is something that they like to call union by rank. I think you've seen this in 61b. If it was never told to you or you didn't realize it, I'll just tell you now. What is rank? Rank is what would the height of my tree be if there hadn't been any path compression? Okay, that's all rank means. Okay. So that's what rank is. What would my height be if there were no path compression? Okay. So it almost feels like cheating. I said, basically what I said is I can't keep track of the height because it's hard to keep track of it efficiently due to path compression. So now what I'm really saying is just pretend that path compression didn't happen and keep track of your height anyway. But now it's not really the height, so let me just call it by a different name, right? So I'll call it rank. But it's like being lazy about keeping track of your height. Okay? So, right. So maybe what I'll do now is I'll write some pseudocode down for, because I know that people have seen this data structure before in 61b. So I don't want to spend too much time on the pseudocode, but I do want to write it down because, just make sure we all are on the same page here. Okay, so we'll have arrays P 1 to n. Pi is the parent of I, and rank 1 to n. The rank of I is the rank basically of item I. And let's say that if the item is not in the let's say. Also, if x is a root, then the parent of x will just be equal to x. So that's how I know who roots are. So pseudocode makes that now he's his own root. So I should set the parent of x to be x. Remember what rank is. Rank is like what would the height of the tree be if there were no path compression, right? So this is just a tree with one node, so its height is 0. So the rank of x is 0. Okay, that makes that. Let's do find. what I'll say is, so this is going to be some recursive code. If the parent of x is just equal to x, return x. Otherwise, I'll say x gets to be find applied to p of x. And then that's path compression, and then I return x. Or actually, I should say p of x gets set to be find p of x, and then I return p of x. So I recursively find upward in the tree. Whatever that recursion returns is my new parent, and then I return my parent. And then there's union. Right? So the first thing I'm going to do is I'm just going to figure out who the roots of my trees are. X gets find of x, and y gets find of y. That's the first thing. And if those two roots are already equal, there's nothing to do. Otherwise, if the rank of x, remember the shorter tree, remember our rank is not really the height, but I'm sort of pretending like it's the height, right? So I want the shorter tree to point to the bigger tree. So let's just pretend that x is the shorter tree. So if rank of x is bigger than rank of y, I'll swap x and y. So now, after I've done that swap, x is either the shorter tree or the trees have equal height. So I'll say, okay, so now what I'll do is the shorter tree has to point to the bigger tree, which means the parent of x needs to get set to y. And if the heights were equal, that means the height of y increased by 1. If the heights were equal, then the height of y has to get incremented by 1. Okay, so that's it. That's the disjoint forest data structure with both union by rank and path compression. This line is the path compression. And the fact that I make sure that the rank of x is smaller before I change the pointer, that's union by rank. Okay? Questions about this? Yeah? Why do you need path compression? Oh, what good does it do? So, I mean, right? Imagine back to when I was storing things as linked lists. Suppose I did a find on x, right? I walk. That takes a lot of time. Then my next operation is find on x. I do all that work again. So if I just spam find x, I take forever, right? So the idea of, and also like, you know, let's say this is right above x is some other node w. If I do a find x, I spent, in the process of serving that request to find x, I touched w, right? So like, if I do a find w later, and after touching w, I eventually went to the root, right? So if I do a find on w later, I have to do all that walking all over again. It sort of seems wasteful because I already touched w last time, and I already found the root, you know, over the course of like walking through w. So shouldn't I already know that w points? Shouldn't I already know who w's like set is, or should I already know who w's root is? So the idea of path compression is, since you're already spending all this time touching these nodes, like I'm already spending constant time touching the node, I might as well spend an extra unit of time changing the node's pointer. So what path compression does is right after doing a find on x, I get this very shallow structure where now all these nodes are right here pointing directly to the root. Right? So that the next time I do a find on any one of these things, I immediately know the answer. That's what path compression buys you. Yeah?
Is there any way that during the union you can also have all the nodes in the smaller tree point directly to the new root?
Oh, you said, is there any way where during a union I can have all the elements in the smaller tree point to the root of the bigger tree? Yes. I could do that. And in fact, what I would get, it's basically almost the same as like this kind of heuristic, union by size for linked lists. I would get the same kind of runtime. So I could do that, but it wouldn't improve my asymptotic runtime. But it'd still be good. I mean, n plus n log n is not bad. Yeah?
How is path compression?
Oh, wait, sorry, let me take you first.
Do you have to swap x and y, or do you just like reassign y to x?
I mean, I can do an if statement. I can say if the rank of x is less than the rank of y, do this, otherwise do this.
Okay.
I mean, it's the same. Yeah?
How is path compression any different from what we did earlier where we started pointer to the head of the list?
So how is path compression different from before, where before I said everyone just remembers the root, right? And the reason it's different is I'm being a little bit lazy. So the problem with that, if I insist that everyone has to always store a pointer to the root, then going back to what you asked, like that would be the same as, when I union two trees, everyone in the smaller tree or the shorter tree or whatever has to change its head pointer. But like that could be expensive, right? It's like potentially I'm doing more work than I really need to be doing. Whereas with path compression, the idea is, look, I'm already doing this work anyway, right? I'm already walking up this path anyway. So why don't I just alter that path? I'm not doing any extra work beyond what I'm already doing, up to a constant factor. So it's being a little bit lazier. So that's one strategy for designing good data structures and algorithms is like you should try to be as lazy as possible, okay? But, be like efficient about your laziness. Okay, I don't know if that makes sense, but that's how I think about it. Okay, good. So now let's try to analyze this. We only about half an hour left. Let me write down some claims. And before I write down the claims, I want to introduce a concept called amortized analysis, which we've already done it, but I want to make it a little more formal. Who's heard of amortized analysis? Is that in 61B? Okay. So just to make sure we're all on the same page. Okay, so we say some data structure supports operation types, let's say operation 1 up to like operation R in amortized time T1 up to TR if for any sequence of N1 operations of type O1 and 2 of type O2, etc., the total runtime is at most the sum I goes from 1 to R of Ni times Ti. Okay? So let's just think about what I'm saying here. So when we talk about like the worst case runtime of a data structure, if I say, for example, like, let's look at binary heaps, right? They support decrease key, delete min, and insert. When I say that the running time of like decrease key is log n, what that means, the worst case runtime of decrease key is log n. What I really mean is you will never spend more than log n time on any decrease key or on any delete min or whatever. When I say that the amortized time is small, it only means that over a sequence of operations, the total aggregate time of doing all the operations is small. It doesn't necessarily mean that any individual operation is fast. Right? So for example, when we talked about the union by size heuristic for linked lists, representing sets as linked lists, right? I said that any sequence of at most m finds and n make sets and n unions takes time at most m plus n log n. Right? Oh yeah?
What's the major distinction between amortized and average runtime?
Average. Okay, so I'll get to that. So the question was, what's the difference between average runtime and amortized? I'll say something about that in a second. So in amortized analysis, the point is, even though in aggregate the total time it takes to do all the operations is low, it doesn't mean that every individual operation is fast. For example, if I did union by size with linked lists, imagine over time I have one set of size n over 2, and I have another set of size n over 2, and I did a union. One of them is going to get put as the tail of the other, and all of their head pointers are going to have to change, which means I'm changing n over 2 head pointers, which takes n over 2 time, right? So there's no way around it. Even though my total time is m plus n log n, in the middle of that, I might have one operation that triggers linear runtime. Okay? The point is that can't happen over and over again. In aggregate, the total time is fast, even though there might be some individual operations that are slow. So that's what it means to have a good amortized runtime. Any sequence of operations is fast. Now back to your question about what's the difference between amortized analysis and average case analysis. So normally, it's just jargon in the field. Normally when people say average case analysis, what they mean in the field of algorithms, if you pick up an algorithms paper in a research journal and you see the words average case analysis, what they mean is that the input is random, and they're looking at the expected runtime of some algorithm on random input. Amortized analysis is not that way. This is still a worst case bound. It's still no matter what sequence of operations I do, I'm fast. It's just that the fast is an aggregate. It's not on each individual operation. Okay? The input's not random here. Average case analysis, when you use that term, it implies you're thinking about random inputs. Any other questions? Yeah.
Does path compression use amortized runtime because it might do more work now, but then in the future it does work?
That's right. Yes. Okay. Yeah, so that's a good point. So I said the reason you're doing path compression is to make future, you're already spending all that time walking up the route now. So it's definitely not helping your time now. It's helping your time for the future. Right? So it's that's a natural way to think about maybe it's helping the aggregate time and why that might be good for amortized analysis. But okay. So I want to write down, though, now the claim. Or the theorem. Any sequence of at most m finds and at most n make sets and unions takes time big O of m plus n log star n. Or log, remember what log, I talked about log star back when I talked about Karatsuba's algorithm, right? It's the number of times you take, what does log star of n mean? It's the number of times you take log base 2 before you get down to 1, right? So basically log star of, say, 2 to the 2 to the 2 to the 2 to the 2 is 5, right? Because if I take one log, if I take log base 2 of this, I get rid of 1, 2. If I take another log base 2, I get rid of the second 2. If I take 5 of them, I get down to 1. And by the way, this number is huge. This is 2 squared is 4. 2 to the 4 is 16. 2 to the 16 is 65,536, I think. Or, yeah, something like that. And then 2 to that is very big, right? So this number here is bigger than the number of particles of the universe, yet log star of that number is only 5. So what that means is, like, in practice, log star is never bigger than 5. Okay? So this is a very small number. It's actually possible to get a better bound than log star n. It's possible to get a bound that involves what's called the inverse Ackermann function, which takes in 2 parameters, m and n. I'm not going to define it in class, but that's actually the tightest analysis. You can prove that it takes time at most, replace log star n with inverse Ackermann. And inverse Ackermann is a function that basically is never bigger than 4 in real life, even though in theory it could go to infinity, but it's never really bigger than 4. And in fact, that's a tight analysis. It's possible to come up with input sequences, with operation sequences that force the algorithm to actually take time, which is that, m times the inverse Ackermann function. So that really is the correct bound. And anyone heard of a person named Bob Tarjan? Okay, one person. So Bob Tarjan is an algorithms person. I think he's a professor at Princeton right now. He's been there for a long time. But he's famous for a lot of popular data structures and algorithms, like the splay tree was co-invented by Bob Tarjan. Using depth-first search to solve all kinds of problems, like linear time recognition of, like, planar graphs, finding bridges. Question?
I was just wondering if in practice log star of a number is never greater than 5, why don't we include it in the final bound?
Why do we?
Yeah.
Because we want to write bounds that are basically true for all n going to infinity. Yeah. That's the only reason. So anyway, Tarjan is someone who does a lot of algorithm stuff. I feel like a lot of what you learn in this class, not all of it, a lot of it, especially the graph stuff, was like done by Tarjan back in the 70s or something. He claims that his proudest result, the result that he came up with that he's the most proud of, is proving that disjoint forest with path compression and union by rank has complexity, which is like inverse Ackermann. Okay, so that's the proudest moment of this person. So it must mean something. Okay, let's now try to prove that theorem. Before I prove the theorem, I want to write down a few claims. So claim 1 for any tree, right? We're storing a collection of disjoint trees, right? Each set is a tree. For any tree, if its root has rank k, this is claim 1, then the tree has at least 2 to the k nodes inside of it. Claim 2 is that the ranks strictly increase as you follow parent pointers. And claim 3 is that the total number across the entire data structure, the total number of nodes, not just roots, but all nodes, of rank exactly k is at most n divided by 2 to the k. Okay? So these are 3 observations about the state of this data structure at any point in time. And I want to say a few words about why these things are true. I don't want to spend too much time on why it's true. But I do want to say a couple words. So the reason why the first two claims are true is induction. Okay? No, so basically, you can induct on the number of operations that have happened so far in the operation sequence. Okay? So let's say that up until now, this statement has been true. Or actually, what I can say, let's go back to the first one. For the first one, what I can say is, if your root has rank k, it became rank k. Where did it become rank k? The only time that the rank goes up is here. If you look at this code, this is the only place where rank changes. Or when you make set, the rank gets set to 0. So when he became rank k, he had some size, right? Whatever that size is. And then any operation that happened after, like a find, for example, or any find that happened after, or any union that didn't change his rank, it's not going to decrease his tree size, right? Find, if you have a root with a tree under it and you do a find somewhere in that tree, it doesn't change the size of the tree, right? If you do a union that doesn't change the rank, then the tree can only get bigger. So whatever his tree size is when he became rank k, his tree size will only stay that way or grow as long as he stays rank k. Okay? So we can prove claim 1 by basically induction on k, where we say our inductive hypothesis is that when a node becomes rank k, its tree size is at least 2 to the k. And then we can induct on k. Is this true when k is 0? Yes. When you become rank 0, it's because you did a make set. Does your tree have size 2 to the 0? Yes, 2 to the 0 is 1. You have yourself. Okay. Now for the inductive step, let's look at someone who just became rank k. How did he just become rank k? It's because he was rank k minus 1, and he got union with someone else who was rank k minus 1. Right? That's the only place where rank goes up. But by our inductive hypothesis, these two trees of rank k minus 1 each have size at least 2 to the k minus 1. So when you put them together, they have size at least 2 to the k. Okay? So that's claim 1. Claim 2 is again induction over the operations, over the number of operations that have happened so far. Right? So suppose that this invariant has been maintained so far, and then now I did a new operation, like I did a find or I did a union. Do I still maintain this invariant? Yes, right? Because when do parent pointers change? Parent pointers change in one of two places. Either I did a path compression, or I did a union, and the old root points to the new root. If I do path compression, remember, up until this point, by my inductive hypothesis, I've been maintaining the invariant that ranks only increase as you go up. If I do path compression, I'm just pointing to some higher ancestor of myself. So everyone above me is higher than me. So if I point even higher, that person is still higher than me. So it's still the case that ranks are going up as I go up. And when I do a union, and I introduce a new edge, well, I always make the smaller rank guy point to the bigger rank guy. So again, ranks go up. Or if they're equal, I increment the parent. So again, ranks go up. So no matter what I do, I maintain this invariant that ranks strictly go up. Okay? So that's claim 2. Basically, as I follow parent pointers, ranks strictly go up. And then the third thing is that I want to say that the total number of nodes of rank exactly k is bounded. Okay? Now, how do I prove? Let's actually write down the proof of claim 3, because the proof of claim 3 requires a little bit more non-standard reasoning. Proof of claim 3. Let's look at the nodes that do have rank exactly k. This node has rank k, this node has rank k, this node has rank k. So each of them has some kind of subtree under it. Let's look at two of them, x and y. Now, each of these, by the way, might be part of a bigger tree. X might not necessarily be the root, right? And Y might not necessarily be the root either. Now, X at some point, though, was a root, right? Let's look at the point in time when X became rank K. When X became rank K, how did that happen? Either K is 0, and it's that. Well, first of all, if K is 0, this is trivial. I'm saying the number of nodes of rank 0 is at most n. There are only n elements of the universe. So really, this is only interesting to prove when K is at least 1. So how did X become rank K? Again, there's only one place where that can happen. That's right here. Right? This is the only place where ranks go up. So X became rank K because it used to be rank K minus 1. Right? And it did a union with some other rank K minus 1 person, which made it rank K. And at that point, it was a root, because only the root gets its rank increased. So let's look at what was X's tree, not right now, but at the time that it became rank K. So this is X's tree at the time it became rank K. And this is Y's tree at the time it became rank K as well. So this is tree Y, and this is tree X. And one of them had to become rank K first, right? So without loss of generality, let's say that X became rank K first. Now, what do I know? I know that the union over all X's of rank K of Tx, this union has size at most n, right? Because there are only n elements in the universe. What do I know about the size of Tx? Claim 1. The size of Tx is at least 2 to the k. Right? And the size of Ty is at least 2 to the k. All of these T's have size at least 2 to the k. I also know that these trees are disjoint. You have to think about it for a second. Why are they disjoint? It's not 100% obvious, because these trees don't exist at the same point in time. Right? This is the tree under X when X became rank K, which was some point in the past. And this is the tree under Y when Y became rank K, which is a tree at another point in time. Things might have changed since then. They might have got union with some bigger tree. There was some path compression. Some of these guys got moved to be not in X's subtree anymore. Okay? But I claim that if you look at these trees defined at those points in time, these trees are disjoint. Why? Well, to say they're not disjoint means that there's at least one element that's in both trees. So let's look at an element in this tree. Remember, X became rank K first. Let's look at an element in this tree. Can it be the case that this element is also in this tree? Well, remember now, there's some path here up to the root. And all these, right, and this guy has some rank, which is K right now. The only way that, right, the only way that X could ever end up, well, basically, for X to be in this tree means that at some point there was, how should I put it? There had to be some sequence of unions where, like, X's tree now is under Y. Right? But that can't happen because of claim 2. Ranks only go up as you go up in the tree. Right? So basically, X is always in X's subtree unless X might potentially do a path compression and point to someone even higher. But the point is, once this element is in X's subtree, its root is always going to have rank at least the rank of X, or strictly higher if it did path compression. And none of those nodes at X or higher could ever possibly end up under Y, because then you would have someone of higher rank under someone of smaller rank, which violates claim 2. So these trees are disjoint, which means that the size of their union is just the sum of their sizes, which is at least 2 to the k times the number of these trees, the number of elements of rank k. So if you move the 2 to the k over, it means the number of elements of rank k is at most n over 2 to the k. Okay. So now I can try to prove this theorem. And I'm going to do it via what's called a charging argument. Okay. And I mean, people have heard of like, keeping a tab at a bar or something, right? I've never done it, but I've seen it in the movies, right? Put on my tab. Okay. So here's how we're going to reason about this. Whenever there's an operation, we do some stuff. Each time we do something, it costs 1 unit of time. Okay? Now, some of that stuff is going to be easy to reason about. I'm going to be able to easily bound it in terms of m and n. Some of it is harder to keep track of. So for some of that harder to keep track of stuff, I'm going to put it on someone's tab. Okay, so who has tabs? The elements of the universe 1 to n have tabs. So item 1 has a tab, so sometimes I'll say put it on 1's tab, or put it on 5's tab, or whatever. And then at the end of the day, I have to figure out how much work did I actually do. I have to add up all the tabs. Right? That's how much money I spent. That's how much time I took. Okay? So I'll keep track of my runtime by basically, the analogy with like being in a bar would be sometimes, I'm one of the people in the party. Sometimes I just pay for something myself. Okay? That's just like normal counting runtimes. Sometimes I put it on someone's tab. And then at the end of the day, I want to ask how much money was actually spent at the bar today. And it's the sum of how much money did I spend plus how much money was on everyone's tab combined. Right? That's the total money that was spent today. So I'm going to do the same thing here. Sometime when I take a unit of time to do something, I'm going to actually count that I did that. I took that unit of time. That's like me paying myself. But sometimes it's hard for me to keep track of. I'll just say put it on someone's tab. So that might sound kind of abstract right now, but once we do it, maybe it'll look a little, you'll understand where I'm coming from or like what I mean here. And in fact, rather than, in this example, it's going to be easier for me to think about, rather than put something on someone's tab, what I'm going to do is in the beginning, I'm just going to give everyone the same amount of money. Or I'm going to give everyone money in the beginning, and I'm going to say, delete it, decrement it from his tab. So everyone gets $100. And then every time I spend 1 unit of money, I'll say, take it from 5's account, or take it from 7's account. Right? And I just need to make sure that no one goes negative. Everyone has enough money to pay for everything. That's basically the same as like put it on someone's tab. Right? Okay. So I'm going to allocate for each item x in the universe, give it, okay, so first of all, before I do that, first I'm going to partition ranks into groups. So there's everyone who has rank between 0 and 1. There's everyone who has rank between 1 and 2, between 2 and 2 to the 2, between 2 to the 2 and 2 to the 2 to the 2, etc. In general, between k and 2 to the k. Okay? So, right, people have ranks. Ranks start at 0, and then sometimes they get incremented over and over again. So, I'm just partitioning rank space into like these different sets, these different intervals that are disjoint. And I'm going to say here, this is like, I'll call this like group K. Group K here is the interval that goes from K to 2 to the K. It's actually the log star of kth group. And now, just let's keep trying. Let's try to reason about this a little more, understand what's going on here. What's the biggest rank any item can ever have? Claim 3 says the total number of nodes of rank exactly k is bounded by n over 2 to the k, which means when k is log n, the number of nodes of rank log n is at most 1. The number of nodes of rank log n plus 1 is at most a half, which means it's 0 because it's an integer. So no one can have rank bigger than log n. Right? So the end point of these intervals are like 2, 2 to the 2, 2 to the 2 to the 2, 2 to the 2 to the 2 to the 2, etc. When that endpoint is bigger than log n, that's it. There are no more groups after that. Right? So let's say 2 to the 2 to the 2 to the 2. This is, by the way, known as like, so let's say 2 up arrow r. 2 up arrow r means a tower of exponentials of height r. So 2 to the 2 to the 2 to the 2 to the 2 r times. I'm done when this thing is like at least log n. 2 to the r is bigger than or equal to log base 2 of n. If that happens, then that's the last group. But that's exactly the definition of log star. Right? So I'm saying, how many times do I have to take 2 to the 2 to the 2 to the 2 to get log n? This is exactly r being log star of log n. Right? How many times do I have to take 2 to the 2 to the 2 to the 2 to the 2 to get n? It's log star n. How many times do I have to take 2 to the 2 to the 2 to the 2 to the 2 to get log star n? To get log n, it's log star of log n. Okay? And by the way, log star of log n is exactly the same thing as log star of n minus 1. Right? Because the definition of log star is how many times do I have to take log before I get down to 1? Well, the very first time I take log of n, I'm at log n. So now log star of that is just 1 less. So basically this is roughly log star n. So the number of groups here, I'm partitioning the ranks into log star n groups. And then what I'm going to do is remember I want to have these tabs for my bar. What I'm going to do is, whenever an item joins a new group, say the group from k to 2 to the k, I add 2 to the k dollars to that item's tab. Right? So this is how I contribute money to people's tabs. Right? Someone starts off at rank 0. Eventually his rank might increase because of this line in the code, and eventually it might increase again and again and again. As his rank increases, occasionally he moves into the next group. Whenever that happens, whenever he moves into a new group because his rank increased, I'll add to his tab. So if he moves into the group, which is the interval from k to 2 to the k, sorry, that should be an open paren. Okay, I'll give him 2 to the k money. Okay, so that's how I'm allocating money. And then the claim will be that the sum over all tabs is going to be O of n log star n. We're running out of time, so I'll prove that next time. Okay. Actually, O of n log star n. And then what I'll show you next time is that there is a way to now reason about the total runtime of all operations, where sometimes I'll pull money out of someone's tab, and sometimes I'll pay straight up, such that I never make anyone's tab go negative. And that's going to end up giving me a total runtime of n plus n log star n. So you'll see that at the beginning of Thursday's lecture, Then we'll finish MST and then start doing dynamic programming.